Why do we want to know the mass of a star? Well, let's go back and kind of review what we've learned so far. We've talked about how to measure their distances using parallax, and then that other technique called spectroscopic parallax, which I said has nothing to do with the first parallax, but it's just another distance technique. We talked about how to measure stars' luminosities. Once we know their distances, then we can get their luminosities. And we talked about how to measure their temperature, if we know the color or the spectroscopic class. And we talked about that temperature sequence, OBA, FGKM. That's the spectroscopic classification system, and it relates to temperature. And how we get their sizes using Stephan's law, and knowing the temperature and the luminosity will then give us the radius. And we also talked about the HR diagram, right? What is it? It's a plot of temperature on the x-axis and luminosity on the y-axis, and it tells us, it shows us that stars occupy a very specific temperature and luminosity range when they're burning hydrogen in their core, which we'll talk about.
So, take a quick review of what the chapter covered. How to measure distance, how to measure luminosity, how to measure temperature, how to measure sizes, and what is the HR diagram for doing much of the above. Now, calculation-wise, we don't know how to do any of this, but this is the theoretical part of astronomy, and these are the way those who do know can accomplish those types of measurements and evaluations.
Talk more about that in the next chapter, but that's essentially what's going on. Most stars, we said, are on this main sequence. And now we talked about getting masses using visual, spectroscopic, or transiting binary stars. So why is mass so important? Well, remember when we were looking at the HR diagram and I was showing you how most stars lie along the main sequence? You might have wondered then, why aren't they all at the same luminosity and the same temperature if they're all burning hydrogen?
You know that answer? That's important.
Well, the reason they're spread out along this thing called the main sequence, the only reason that they're spread out like that is because all the stars that we were looking at have different masses. So together with their initial composition, the mass defines pretty much the entire life cycle and all the other properties, luminosity, temperature, size, all that is determined from the mass. Also,
very important.
What's going to happen at the end of its life, the end result, is determined by the mass. So stars that are as massive as the sun, they're going to be right here with 1 solar luminosity and temperatures of just under 6,000 degrees. But stars that are 5 solar masses sit further up on the main sequence, and the ones up at the top are the most massive.
That was determined because this is where our sun is. So we have used the mass of our sun as the benchmark, and the number 1 in luminosity is equivalent to our sun. These are other different suns as you go along the universal scale.
The dwarf stars, not only are they smaller, but they're less massive. So lower mass stars are going to be down here when they're burning hydrogen. Higher mass stars sit up here. Now this is another diagram. This is not the HR diagram, but this is showing luminosity now versus mass. Remember, the other one was luminosity versus temperature. But if we were to plot luminosity versus mass, we would find that main sequence stars make almost a straight line here. Now it's not exactly straight. It's actually, this is a log scale, right? And the mass is not. And so what it really corresponds to is that the luminosity is proportional to the mass taken to the 4th power. Now why is that? Well, what this means is that if there's more mass to the star, then there's greater gravitational pressure placed on the core of the star, and that means the temperature in the core is even higher, And those nuclear reaction rates that we talked about happening in the center of the sun, right, those happen even faster and essentially leads to higher luminosities. So more massive stars are going to be more luminous, and the mass has a big effect on the luminosity. You can see here. So it's mass to the fourth power tells you the luminosity.
More massive stars have greater luminosity.
So mass really tells you, how bright that star is going to be. Now, that's also helpful because from the luminosity and the mass, we can figure out how long a star will live, right?
I will cut this short at some point.
The lifetime of a star is proportional, that's this little symbol here, it just means it's proportional to how much fuel you have to burn divided by how fast you're burning the fuel, right? Now, for a star, how much fuel you have to burn is its mass, right? And how fast you're burning the fuel is its luminosity, right? The luminosity is the energy that's being released during those nuclear fusion processes. So the luminosity is a direct measurement of how fast it's burning the available fuel. So the lifetime, or the amount of time a star can live, depends on the mass divided by the luminosity. Now remember, I just told you that luminosity actually goes with the mass of the star to the fourth power if it's on the main sequence. So I can replace the word luminosity here with mass to the fourth power. So the lifetime is actually proportional to the mass divided by the mass to the fourth power, and you know that you can just cancel one of the numbers there and it becomes 1 over the mass.
Okay, don't worry about that.
Mass cubed. So how long a star lives goes as 1 over the mass of the star cubed. Now that's kind of interesting because what it says is that if a star has a bigger mass, if this number here is bigger, its life, or the amount of time it can live, is actually a lot shorter. So more massive stars actually live shorter lives. So bigger, massive stars live shorter lives because they burn their fuel so much faster. And, if you increase a star then by a factor of 2 in mass, say, it's actually going to burn through its fuel so fast that it's going to live 8 times shorter an amount of life, right? Because it goes as mass cubed. So that would be 2 times 2. 2 times 2 times 2, right? So if you think about that, you can see that a little, more massive stars, they're going to live much shorter lives. So a star